In this video, we'll talk about deterministic finite automata. So to start off, let me write DFA, and this just stands for deterministic finite automata. Deterministic finite automata. Okay, so when we talk about DFAs, we are talking about machines, and these machines are very specific and very limited in their capability. And you have also the word finite, this word finite in the name of these machines, because that refers to the fact that they have finite states and a finite alphabet, input alphabet. Because these things, what they do is they read letters or alphabet. You can think of it as letters almost, of, let's say, a string, and they go to different states. And based on the definition of the machine you defined, they might accept or they might not accept the string that you're reading. So let's actually look at how this machine looks like. So this machine, let me do it in pink. This machine is defined as a set of these five things, and I should say a 5-tuple. This Q, I'll talk about what these are in a second, but sigma, delta, S, and F. So first off, let's talk about Q. So Q is a finite set of states and it's very important you keep in mind this is finite, so you can't have unlimited number of states based on what you wish for. That's not possible in a DFA. So yeah, let's also talk about sigma, which is a finite input alphabet. And when I say alphabet, I really mean alphabet. Yeah, and when we say alphabet, it's talking about symbols. So for example, A, B, C, or 0 or 1, alpha, beta, however you want to define this alphabet, it's a set of input symbols. So let's call that an alphabet. We also have delta, which maps Q cross sigma to Q. So it takes in an input, one state and one letter in the alphabet, and it gives us another state. So this is a function. This is a function that maps states to other states based on the symbol it's currently reading. This machine is currently reading, right? So yeah, that's what this delta is. It's a transition function. Transition function. Okay, and then we have S. Oh, that looks like a delta. Okay, so this S is the state we start with. So starting state. Oh no. Starting state. And of course, this is an element of our states Q, and F, this is the set of accepting states. And of course, this is similarly a subset of Q, because accepting states are also states. So yeah, this is everything we need to define a DFA. It's this 5 tuple. When we have it, we have this machine M, a DFA, and there's a couple other ideas we need to consider. So let me write on a new page. We talk about accepting strings, and I was mentioning this earlier. We might care about whether or not a string is accepted or not accepted, in other words, rejected, after reading it bit by bit. And we know whether or not it's accepted by whether or not our machine is currently in a state that is accepting after reading the whole string. So let me actually write it out as an example. Strings. So let's talk about strings. So let me write this example. Right. We have a set of states. Let's say Q is the starting state, state 1, state 2, state 3. Yeah, let's just say we have these 4 states, and our input alphabet we can say is 0, 1. Yeah, let's say it's 0 and 1. These are the symbols in our input alphabet. And delta, well, we'll see it when we draw a picture. I'm not going to write delta based on its type signature here. And the set of accepting states, let's say starting state we already know is this one, so I'm not going to write that. The set of accepting states, let's say, is only 3. So 3 is our accepting state. Okay, so let's draw this DFA we've defined. So let me draw it in red. So this is the starting state. We just draw an arrow coming into S to indicate that it's the one we start with. It's the starting state. Now, whenever we have accepting states, we have to draw it with 2 circles. So, you know how we drew this S with 1 circle? Let's say we draw 3 here. We'll draw it with 1 and 2 circles because it's accepting. Let's draw 1 here and 2 here. Let's say first we read 0 and we get to 3. Then we read 1, we go to 2, and then we read 0, we stay at 3. Yeah, and then we read another 1. Let's say we go to 1, and then we read 0. We stay at the same state. Okay, so for 1, let's say it stays there for indefinitely. So this is sort of a rejecting state here. This is also sort of a rejecting state, but it's still, in transition. Yeah, I'm trying to find meaning out of this DFA I just defined, but I think I just defined this random DFA, which doesn't have that much meaning to me, at least right now. But nonetheless, it's still a valid DFA. So let's say it goes here after reading one. Okay, let's say this DFA is defines, okay, if you read all zeros, then it accepts. And if it reads at least two ones, it also accepts, right? Let's say both 1 and 3 are accepting states. Okay, at least there we have some meaning now for this. So at least two ones or all zeros. So that means you accept string. All right. So let's say we have a string s, and that string is 0, 1, 1, 0, 1. Let's see where it goes. So 0, 1, 1, 0, 1. So it ends up in an accepting state because it has at least two ones. At least two ones. So, yep, indeed we accept it as per this DFA, and also that's the rule we defined. What if we had 0, 0, 0, 0? Then it's just here, state 3, 0, 0, 0, 0, and it accepts. What if it was like 0, 0, 1, 0? Well, it's 0, 0, 1, 0. Well, now it's not all zeros, and it's not at least two ones. So it gets rejected. It's in the rejecting state here. All right, so based on the rule we defined, it seems like this DFA carries out what we needed to do. And that's an example of what strings are and how we can either accept or reject a string based on the machine we've defined. Okay, so that's all about strings and accepting and rejecting. Let's talk about languages. All right, so languages, we say a language LM is the set of all strings is the set of all strings that this machine M accepts. Okay, and another idea here is that if for some language L prime, if we have some kind of L prime and there exists some DFA M such that L prime equals LM, then we have the case that L prime is regular. It's a regular language. Let me get that out here. let's see. So really, that's all that DFAs are. And in the future video, we'll also talk about an equivalent idea of NFAs, non-deterministic finite automata, which are again equivalent to deterministic finite automata, only their representation is a little different and sometimes more convenient for us to make diagrams and write down, because we can express things in fewer states than with DFAs, perhaps. But that's what we'll look at later on. So thanks for watching.